gases, experiments that were performed essentially before examining the alkali resistance of the thin film. Experiments were set up to exercise and validate the necessary equipment, procedures, and measurements needed to determine alkali damage. Two readily available bulk glasses of fused silicon, magnesium fluoride, calcium fluoride, and aluminum oxide were introduced as optical windows into the gain cell emulator and exposed in stages to atomic rubidium. Changes were observed in the optical window color, weight, surface roughness were measured. The optical damage to the materials was also assessed by observing changes in laser optical transmission and energy throughput using optical parameters and any surface changes to the material as well as visual inspection. In step one, we basically introduce samples into the. In the next slide, we introduce, as part of the experimental procedure, samples into the gain cell emulator. And we put the witness samples into the clamshell assembly and load them into the gain cell emulator, and rubidium metal helium is introduced into the gain cell emulator. We place the gain cell emulator, the sealed gain cell emulator, inside an oven and heat the atomic alkali and helium buffer gas up to 200 degrees Celsius for 7 days. And also the option of firing the laser at the high power at 1 kilowatt per centimeter squared in the gain cell for 7 days. However, if none of the materials can survive the hot alkali, the reasoning is that it would not make any sense to fire the high power laser into the gain medium. So this is the witness sample holder, the clamshell assembly, showing the groove positions, designed to improve circulation of the rubidium vapor while the assembly is inside the gain cell. In the background there is stainless steel samples used for fitting and just to carry out the experiment set up initially. And the next slide shows the DPAL emulator design. To the left, you have an aluminum enclosure, stripped heater, a corrosion test fixture, and a retainer, and just the ability to be able to observe the emulator inside the sealed oven. So as you can see, the small form factor of the gain cell emulator to the left in the next slide. And so this is the balance of the experimental setup. As you can see, temperature readout at 200 degrees Celsius, and the sealed DPAL emulator in the oven off to the right. So we move to step 2 in the experimental procedure, which is the post-exposure analysis after 7 days or whatever our prescribed time limit is. And so we examine the witness changes in the witness sample after alkali exposure, optically, just by visual inspection of cracks, pitting, any color changes, changes in surface morphology, surface roughness, changes in weight of the sample on a OHAS weight scale, high resolution, milligram resolution weight scale, and the optical transmission, one of the most important of these tools, a dual beam intensity monitoring system using a helium neon and TI sapphire laser. The next slide shows the setup for the measurement of the optical power throughput. As described before, the dual beam intensity monitoring system consists of primarily a Heine 632.8 nanometer Heine helium neon laser, 780 nanometer TI sapphire laser, steering mirrors, resize and telescope as far as the optical beam path through the iris, through the witness sample, which have been either as a reference sample or a one that has been exposed, into the photodiode of the optical photometer and or measuring the optical power transmission. As part of the measurement procedure, before each optical window is placed in front of the laser for optical transmission measurements, the power transmission at near and far field were first measured. A total of 26 measurements, minimum, maximum, and average power transmission computed at near field, and 26 measurements at far field are taken before introducing either the reference unexposed optical window or optical window exposed to rubidium vapor. An additional 26 measurements, minimum, maximum, and the average power transmission were computed for each sample and then taken at near field and far field, this time after passing through the optical window. The maximum power of the laser beam used measured at either near or far field was less than 1 milliwatt for the 632.8 nanometer Heine laser and less than 2 milliwatt for the 780 nanometer TI sapphire laser with a plus or minus 10% measurement accuracy. The next slide shows results of optical power transmission measurements for this 632.8 nanometer helium neon laser probing beam, and the measurements are within plus or minus 10% arrow. The reference sample before exposure of fused silica had a transmission greater than 90%. When exposed, transmission dropped to over 80%, and so on. So this is just an example to show that within one standard deviation, the optical power transmission reduced after exposure to the atomic rubidium. The next slide shows from the optical power transmission of the TI Sapphire 780 nanometer probing laser. The measurements are within plus or minus 3%. Slightly over 90% for the reference sample, followed by a drop to over 80%, and due to exposure to the atomic rubidium, and the measurements are within one standard deviation of the mean. The next slide shows the optical transmission. In addition, Table 4 shows absorption at 780 nanometer, which is the atomic rubidium pump resonance wavelength, appears to be consistently greater than at 632.8 nanometer for all fused silica samples, with a maximum optical transmission loss difference of 8% between both wavelengths. The maximum weight gain, potentially owing to rubidium absorption into the fused silica surface, was detected in fused silica at 0.036 grams. The initial weight of samples are the reference sample weights for fused silica, sapphire, magnesium fluoride, and calcium fluoride. The transmission losses at 780 nanometer in fused silica are suspected to be due in part to the absorption by monolayers of rubidium diffused into the silica network. In addition, the near-field percentage laser optical transmission through magnesium fluoride at 780 nanometer were within 3% between samples and did not represent a statistically significant difference. However, for fused silica, the differences in transmission between samples varied as much as 10% at 632.8 nanometers for samples S3 and S4, The photometers used is known to have an accuracy of plus or minus 10% in measuring the laser beam intensity. The next slide shows results of exposure to atomic rubidium vapor in the form of optical window damage. In the case of calcium fluoride, cleavage of the calcium fluoride occurred after exposure to atomic rubidium. The calcium fluoride optical windows became brittle. Uh, the control temperature ramp were within specifications for ramping up and ramping down in temperature, so no thermal shock is indicated. B, it shows the browning of the DPAL gain cell emulator low-grade quartz optical window due to atomic alkali diffusion. And you can also notice cracking of the gain cell, and so it's just an example to show that really the atomic rubidium does affect the uh, material, and the quality of the material is very important and is resistant to atomic rubidium, hence the quality of the thin film as well. In the next slide, figure 32 shows the optical window damage of fused silica and calcium fluoride optical windows. In the next slide, figure 32 shows the optical window damage of fused silica and calcium fluoride optical windows. So in A, the surface roughness of the calcium fluoride optical windows was measured using the nanoscope, atomic force microscope at New Mexico Tech Department of Materials Engineering. The AFM will image down to 10 nanometer resolution of a sample surface. As you can see, there are images of the unexposed and the exposed calcium fluoride witness samples, and the unexposed surface roughness statistic versus the exposed surface roughness statistics. The root mean squared roughness of the unexposed sample was 4.361 nanometer, plus or minus 1 nanometer, peak to valley. And for in B, the exposed sample was surface roughness was roughly 10.032 nanometer, plus or minus 1 nanometer peak to valley. Effectively, what you have is a increase in the surface roughness of the material, in this case the calcium fluoride, due to the atomic rubidium. The increased surface roughness can potentially lead to greater wavefront distortions, reflections of the output laser beam due to scattering. The ability to measure this parameter really provides a quantification for thin film coating analysis and selection. However, the order of magnitude of these, the surface roughness with regard to the wavelength, is so small that there is no optical transmission loss that's appreciable expected from this change in the surface roughness in this case.